All right, the second thing you need to be able to do on this test is you need to know how to make and how to read an electrophoresis. So this is a picture of a completed electrophoresis. Now, what it is, these little black things here, these are called wells. And the wells in an electrophoresis is where you're going to put your samples. You put your samples in the wells. This is a gel, like it's called agarose. It's made from algae. And three-dimensionally, it would look like this. It'd be like a slab of gel, and these little holes would be your wells. And this is where your samples would go. Now, here's what you would do. You would load your DNA samples into these wells, and then you put your whole thing into a buffer solution, which is sort of like a saltwater solution. So it's a liquid. It's sort of salty, right? And we're going to turn on the power. We plug this into a power supply with a negative charge at the one end. And by the way, it's super important that the negative charge is at the end where your DNA is, because DNA itself is negative, and opposites attract, and like charges repel. So if I put the negative electrode at this end and the positive at this end, there's basically going to be 120 volts of electricity running through this liquid. And all my DNA samples, because they don't like the negative side, are all going to start traveling towards the positive side, like this. But here's the key. Depending on the length of the piece, this is why it says base pairs over here. Let me erase all this mess. Notice how this says 1200 BP. That's how many base pairs or how many letters long each DNA is. Well, it's sort of like everybody starting a race at the starting line, and I say go, and everybody starts running. Well, the big, fat, heavy pieces of DNA that are really long are going to travel really slow. So even though we all started in the same place, the lighter the piece, or the shorter, I should say, the piece of DNA, the farther it's going to go. So in this case, the shortest piece traveled almost to the end. Now, it's really important in an electrophoresis, you only run it for like 45 minutes. If you were to like turn this on and run it overnight, all the pieces would make it to the end. Just like the slow fat person's going to eventually finish the race too. So everything would like run off the end and be floating in the gel, and it would be useless. So you only run this for like 45 minutes, and then you have to stain it so you can see the DNA. And then you would get something that looks like this with a band pattern. So the thing on the left is called a standard. And a standard is a piece that we already know the size of all the cuts. So in this case, they're telling you this is 1200, this is 1000. So one thing I could ask you to do is I could ask you, how big is this piece of DNA that started in well B? Your answer would be, oh, it would be 800 base pairs long. How do I know? Because it traveled the same distance as the standard that I know that piece is 800 base pairs long. How big is this piece? Oh, it's 200 base pairs long. So that's how you would read an electrophoresis. Now, I could ask you, and we do, this is a practice problem here, where I could ask you to draw one yourself. So you'd make the cut. So in well A, they want you to not cut the DNA at all. Now, the DNA, this is that same piece of DNA from the original, is 50 base pairs long. So if I don't cut the DNA at all, at the end, this DNA, this whole big giant piece, is not going to travel very far. You would be asked to label, remember, negative, positive, and the DNA would start traveling as soon as you turned on the power. And I'm going to just make up a scale. Since I know my biggest piece would be 50, I'm just going to put 50 here. 50, 40, 30, 20, 10, and let's just say 5. So at the end of my electrophoresis, when I turned off the power, I would end up with one band here at 50, meaning it wouldn't have traveled very far. Again, we can change how long we run it, and we can change the thickness of the gelatin that we use so that our bands will move. If we have really giant bands, we can make our gel very dilute, with really big pores, really big holes in it, so the DNA can travel more easily. Whereas we can use a thicker gel if our pieces are smaller. Now, second one, cutting the DNA with Hind 2. Well, Hind 2 cut it here, right in the middle. And it gave us a piece that was 25 and another piece that was 25. So if in B I put some DNA that had been mixed with that enzyme, I would basically get one band here at 25. It would travel farther than the band that was the DNA that wasn't cut at all, but I would actually only see one band since both pieces are the same size. What if I cut the DNA with Hey3? Well, Hey3 cut the DNA over here. CCGG. If I count this, 1, 2, 3, 4, 5, this is only 5 base pairs long. And this other piece would be 45 base pairs long. So I would get 2 bands if I cut it with this, but they wouldn't be like this one where they went to here. I would get 1 band all the way back here at 45, and I would get 1 band way up here at 5 for my 2 pieces of DNA. 1, 2. And finally, if I was to cut it with all of the enzymes, both enzymes, and I load that, so I put both enzymes in a tube with this DNA, where would I get the bands? And it's getting a little messy, but I would get this piece, then I would get this piece, and then I would get this piece. Now again, you could literally count the letters if you wanted to, but remember, this was already 25, and this is 5, and technically that means this has to be 20. So I would get 1 way down here at 5, I would get 1 at 20, and I would get 1 at 25. This is pretty sloppy, but that's basically what you would get. And if you were concerned that I couldn't tell where you drew your bands, you could write the numbers in just so I could see. Remember, they should all add up to 50. If the whole thing is 50 long, then every single one of these should add up to 50, your bands. You can't have more DNA than you started with. So this is one version, and in my next video, I'm going to show you another version of this that you could see.